Here I'm going to be looking at stoichiometry. Stoichiometry basically tells us the ways in which reactants react together to form products. And from that we're able to work out the actual amount of products formed or the actual amount of reactants that have reacted given certain data. So we're going to be looking at systems in which reactants react to form products and basically looking at the relationship of the reactants. That is, the quantities in which they react. We're going to look at the reaction of methane with oxygen, so the combustion of methane. So where we take methane, react it with oxygen and form carbon dioxide and water. This isn't balanced, but we're going to balance this now, which is really important part of the stoichiometry of the reaction. So we've got one carbon and one carbon. We've got 4 hydrogens, so therefore we need 2 H2O molecules. If we've got 2 H2Os here, that means we've got 2 oxygens, and we've got 2 oxygens there, which is 4 oxygens, so we need 2 on this side here. So this next part involves the stoichiometry of the reaction. So we're looking at how much oxygen is needed to react with methane. Well, I'm going to go through this in a bit of detail. Methane looks like this. Oxygen, like this. And we know we have 2 oxygens. Essentially, when I have a methane molecule, let's just say I reacted with 1 molecule. We know that's not going to happen because if I had a tiny amount of methane gas, I would have billions and billions of methane molecules. So what this means is that for every 1 methane molecule, I need to have 2 oxygens. Because while the carbon can form carbon dioxide, no problem, the 4 hydrogens that are present in methane need to have extra oxygen atoms to form the 2 water molecules, because those 4 hydrogen atoms need to form product. And it just so happens in this reaction that it forms carbon dioxide and water. In fact, when you burn any organic fuel, you get carbon dioxide and water, provided there's enough oxygen. So the main thing from this is, whenever we write a balanced equation, yes, it means that we've got the right number of atoms on the left as on the right, but more importantly, it tells us that for every 1 methane molecule, I need 2 oxygen molecules, and it gives me 1 carbon dioxide molecule, and it gives me 2 water molecules. That is called the mole ratio, because I could equally say, rather than just saying I had 1 methane molecule, because let's face it, when I react methane, I'm never going to be just reacting 1 methane molecule. I have 1 mole of methane reacts with 2 moles of oxygen to give me 1 mole of carbon dioxide and 2 moles of water. And this is called the mole ratio. It's really important. What we're going to do now is we're going to look at a question involving methane. Let's say you had 27 grams of methane and we're asked what mass of water was produced. Okay, we're going to go through the steps on how to work that out. The first thing, and one of the most crucial steps, is you work out the number of moles of the species that you have. So if you've got 27 grams of methane, we work out the number of moles. That's step number 1. So the number of moles is equal to mass divided by mR. The number of moles of methane here, the mass is 27 grams divided by the mR of methane, which is 14 plus 4 hydrogens, which is 18. So 27 divided by 18 is 1.5 moles. That's how much methane we have in the reaction. Important figure, okay? We've got 1.5 moles of methane. If I wanted to know the number of molecules of methane, I would multiply that by Avogadro's number, which is 6.02 times 10 to the 23. But I don't want to know the number of molecules because we're just happy dealing with the number of moles for now. The next crucial step is using the mole ratio, the most important step. So, according to the mole ratio, 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. Really important. Now, we're only interested in the methane and the water, because that's all we're asked in the question for now. So, according to the mole ratio then, from methane to H2O is a 1 to 2. That basically means for every 1 methane molecule I have, I get 2 waters. But in this reaction, I don't have 1 mole of methane. In this specific reaction, I've calculated that I've got 1.5 moles of methane. So I need to write that out. I've got 1.5 moles of methane So therefore, the amount of water produced from 1.5 moles of methane is going to be twice that. So it's going to be 1.5 times 2, which is 3. So I know that 1.5 moles of methane produces 3 moles of water. So I've got 3 moles of water produced. Going back to the question then, I'm asked what mass of water is produced. Well, there I need to go and rearrange my equation for moles and mass. So mass H2O, well, mass equals mole times mR. So we need the mR of H2O. We know that we've got 3 moles, and the mR for water is 18, because it's 16 plus 2 by 1, which is 18. So 3 by 18 is equal to 56 grams of H2O. There, we've answered the question, we've used the mole ratios. So just to recap then, we start by looking at a balanced equation, then writing out the mole ratio here, then working out the number of moles of a substance we had, really critical. Then we used our mole ratio, and we applied our mole ratio to the question, really important. Then after applying it to the question, we just simply worked out the mass given the number of moles that we had to get our answer. There's a detailed explanation on the notes part of the website. Okay, so we've looked at reactant masses and stoichiometry in a fairly straightforward question. Answering the question by first principles is always a better way of understanding what you're doing. And if you understand what you're doing, then you stand a better chance of getting the questions right in the exam.